my last lecture, I had stopped at a point where I had described the output of an ultra short pulse laser. Okay. So, we had got a pulse output in the femtosecond range, and it was a train of pulses with a repetition rate, and I had just compared the average power of a ND glass and a titanium sapphire laser. So, we go back to that point. So, here as I describe, this is the train of pulses which has a repetition rate, and in ND glass you get somewhere around 50 milliwatt. These are some typical values, and titanium sapphire you get around 200 milliwatts. Okay. And out of that train of pulses we have to select a single pulse. Okay. So, here I just give you a comparison of ND glass and titanium sapphire. Okay. So, the repetition rate in case of ND glass is around 100 megahertz. So, you get a train of pulses of 100 megahertz. In titanium sapphire you will get somewhere around 70 megahertz. Now, this value is dependent on how you have placed your cavity mirrors, etc. So, the length and all will depend on the placement of your optical objects, and yes, so the length of the cavity or the resonator cavity will change accordingly. So, that is how you get that how many megahertz you are likely to get from at the output. Then the bandwidth of the output pulse is, so in case of ND glass 10 nanometer, which is expected because ND glass, now ND glass does have, if you remember the last slide, somewhere around 22 nanometer is the full width half maximum of the spectrum. For that ND glass medium. Now, here what I am speaking of is the spectrum of the output, laser output. So, you had an ND glass which had a larger bandwidth than 10 nanometer, but then the total bandwidth has not been utilized, or the bandwidth may have been squandered away at some points in the oscillator. So, you never get the the full bandwidth of that gain medium. So, the output pulse say has a 10 nanometer bandwidth. Similarly, for titanium sapphire, though you have started off with a much higher spectral bandwidth, you do get somewhere around 100 nanometer. And this corresponds to a wavelength, to a pulse duration of 200 femtoseconds, while in case of titanium sapphire it corresponds to a pulse length of 10 femtosecond. So, this comparison you can see titanium sapphire we do expect a shorter pulse. From ND glass it is a longer pulse as compared to titanium sapphire. Okay. But still 200 femtosecond is still under the category of ultra short pulses, ultra short pulse. And the center wavelength in case of ND glass is 1.06 micrometer, as you know, and the center wavelength for this is 800 nanometer. Okay. So, 800 nanometer is the center wavelength, and the wings of course add to the bandwidth that you speak of. Now, the output, so we are interested in one single pulse of this. Okay. So, what does that single pulse look like? The single pulse looks like this. This is in the time domain, and it is a sec h square pulse. Okay. So, it is not really a Gaussian pulse. Generally, you get a sec h square pulse from oscillator like the one I have described just before. Okay. So, the intensity is here, and this is the time, and this is what the structure will look like. So, it has a spread in the wings, and it is much more peaked than say a Gaussian pulse. Okay. It has got a narrower structure, And in the frequency domain, obviously it will be narrower. This is, it will have a similar kind of structure, which is also a sec h square profile, and it's much narrower here. Okay. This is in the spectral domain, while this is in the time domain. Okay. So you could write in the time domain something like this. This is given, I intensity I is equal to I0 sec h square t by tau. T is of course the time here, and tau is a parameter which gives you the full width half maximum at this stage. Okay. So tau is related to the full width half maximum as 1.76 tau. Okay. So this is what a sec h square pulse look like. So one pulse out of that train of pulses looks something like this. Now what do we have to do? We have, say, achieved our dream pulse. That is, suppose you look at this diagram again, I just bring it up again. This is the ultra short pulse, and you have got it in the femtosecond range, and the beam is has a nice cross section. The beam or the pulse has a nice cross section like that, absolutely circular with a Gaussian profile. Okay. See, the beam cross section may have a Gaussian profile, but your time has a sec h square profile. Okay. So this is the spatial cross section, spatial profile of the pulse, which may be a Gaussian, and it's a nice circular beam like that. So, and you have a good spectrum. You know, this pulse, the time pulse involves a good spectrum. In case of titanium sapphire, 100 nanometer. In case of ND glass, 10 nanometer, which is not bad. Of course, you can work with it. So here I have got the pulse that I desire from my oscillator, that is here. Now I have to go to this stage, the stretching stage. That means I have to stretch my pulse in time from a femtosecond to, say, a nanosecond. It would be ideal if I can go up to nanosecond. Maybe it's not always possible. You'll be in the picosecond range like that, in hundreds or 200s of picosecond. But if I am able to go up to the nanosecond range, I would have achieved my dream stretching, if you can call it that. Okay. So now I will describe this stretching part. How do I manage that? Okay. So in this, as I have said before, I am stretching the pulse. That means I am giving a dispersion to my spectrum. Each of those frequencies, each of those wavelengths have a phase difference between them. That's why I show it in this kind of a colored, red on this side and blue on this side and yellow in the center. So all these frequencies have stretched out in time, but I have not lost the frequencies. So all the frequencies that come within a 10 nanometer or say a 100 nanometer, they are all there. All those frequencies, that bandwidth in the spectrum remains, but I have only placed them at different points of my time profile. Okay. So my bandwidth should be conserved. That is my aim. How far it is possible and how far we can do it, that is to be seen. Okay. So let me go to the stretching part. Okay. So if you remember the Nobel Prize winning experiment which I described before, it stretches in a optical fiber. Okay. So what do I do? I have an optical fiber in which I can stretch. I can also use a grating which will help me in this stretching process and giving me a group velocity dispersion. Okay. Both can be used, but so let's compare both of them. So in a stretcher you have the optical fiber and the grating. I am just talking about the optical fiber. Okay. What are the advantages? It is compact, simple and easy to integrate. Okay. So, you can understand, it is just a bundle of fibers and you just keep it in one corner of your laboratory. And at the ends you can plug in some lenses or a coupler which will couple the laser light into your fiber here, like this. You are coupling the laser light here, it goes through all that, gets the dispersion that is required and then comes out from this end. Okay. And it is not very costly, it is low cost, fibers are not very costly, though, and all these fibers are single mode fibers, okay, not multiple mode, they are generally single mode fibers. In any case, they do not cost much. So, what I need is all those wavelengths, all those frequencies can pass through this. It allows all the frequencies to pass through without attenuation, but giving the dispersion that I require. So, the moment it passes, the frequencies pass through any material, here it turns out to be the fiber, it will give you a positive group velocity dispersion. So, it will give you a positive GVD. So, that is where the fiber is used. And as you can see, alignment is easy and flexible, that you can also understand. Okay. But what are the disadvantages? Disadvantage is whenever a beam of light is passing through a fiber and it has pretty high intensity, nonlinear effects like self-phase modulation, once again, the self-phase modulation was attractive in case of an oscillator, but which shortened the pulse because you wanted a short pulse from an oscillator, but it is not so attractive in the stretcher which is in this fiber. And self-phase modulation will increase the length of the pulse, and then you have other nonlinear effects like stimulated Raman scattering, and it has its own problems, which is this. We do not want any of these nonlinear effects, but you cannot help it, we are at a high intensity. And then losses due to fiber coupling, bending or absorption, okay, these losses also do come into the picture. Though the cost is low and it is easy to couple, but still you do have some absorption, and when it is coupled, when the light is coupled into this fiber, there are certain losses. So, you do not want to lose energy, the energy that you have got from that oscillator and that you will be amplifying in the medium, in the amplifiers which will come through. You want to conserve all that energy because in the final go you want a large peak power. So, this is one of the disadvantages. May not be ideal for broad spectral ranges. Okay. Broad means, okay, so it depends on the kind of fiber you are using, the material of the fiber. It may be clipping off some of the spectra. Some of the spectra, you may have a center wavelength, but the sides may be clipped off by the material of the fiber. And the moment you clip off spectrum means you are losing, you won't be able to come back to the original short pulse. Okay. So, spectrum has to be conserved in whatever way. So, these are the advantages and disadvantages, not that it doesn't, the fiber doesn't work, it does work, it does give you a long pulse and in a nanosecond scale. But finally, in all the systems that have been used till now, they all prefer the grating. The grating in spite of lots of disadvantages. Okay, let me explain the grating, then you will know what are the disadvantages and why it is preferred. Okay. So, in the final go, the grating is used. One initial reason is that the compressor which uses gratings is compatible or a conjugate of the grating here in the stretcher. So, the stretcher gratings and the compressor gratings have to be compatible with each other. while the compatibility is difficult to achieve if you have a fiber in the stretcher. Okay. So, anyway, we will concentrate more on the grating thing. So, let me just tell you. So, the grating is, of course, as you know, it has so many rulings, it has grooves, and this is the normal, and the grating equation is given by m lambda is equal to d sine theta I plus sine theta d. Theta d is the diffraction angle, all measured from the normal. This is the diffraction angle. This is the input beam. Theta I, yes, theta I is here. Theta I is the input beam, and this is the diffracted beam. Okay. So, you are getting a angular dispersion. So, this angular dispersion has to be converted into a long pulse length. Okay. So, you are going to make use of this angular dispersion to get a longer pulse length. So, here is lambda is the wavelength, theta is the angle of incidence, theta d is angle of diffraction, and d is 1 by n, the distance between adjacent grooves. Okay. Distance between adjacent groove means, say, the first this groove and this groove. What is the distance between them? That the small bit here, that is d. Okay. This distance shown in red, that is d. And that will be inversely proportional to the number of lines per unit length. Okay. So, number of lines means number of grooves per unit length. So, d is equal to 1 by n is equal to distance between the adjacent groove, and n is the number of lines per unit length. Generally, a grating is qualified by the number of lines, or that is the parameter of the grating, by the number of lines per mm. Per unit length is in terms of mm, millimeter. So, within 1 millimeter of that grating, how many grooves do you have? You must be knowing all this, you would have studied it in optics. Gratings have been used for years and years together. So, nothing new in this, it is just being used in this case, in case of a stretcher. Okay. So, let us go ahead. Now, what does the stretcher look like? Okay. Just remember, we are trying to stretch the pulse in time from femtosecond to nanosecond. We are trying to stretch in time. Okay. So, what do we do? So, what we have to do is, you have this is one grating and this is another grating here. There are two grating placed in this sort of a way. It is called anti-parallel. So, if they were parallel, the gratings would have been like this. But then, you know, one of them is turned by 90 degrees. Okay. So, now you have one like this and one like this. Okay. These are called anti-parallel. So, I have one grating here and I have one grating here. Okay. And in between them I have two lenses, and they are placed at 2f. The distance between them is 2f. F is the focal length. Okay. So, here I have given you the focal length part here. Focal length is here. So, in total your stretcher consists of these two lenses and these two gratings. So, with this I am going to get a long pulse in time. The two lenses, you will know what is the use of these two lenses. They are placed in a unit telescope. They form the unit telescope. That means there is no magnification as such. Magnification is just one. It is called, the two of them together forms a telescope with a magnification of 1. Now, my input beam here, as is shown here, this is the input beam. Input beam is shown here. So, it falls onto this mirror, this grating, and it gets diffracted along this. Okay. So, I place it that way, I get the diffraction along this away from the normal to the grating, but okay, no, along this axis. Okay. So, now I have a whole lot of frequencies, whole lot of wavelengths which are passing through this. Now, if I had just one grating, the first one, Z1, and all the frequencies are spreading out, and I let them travel over time, over a big distance, a very big distance. And after that big distance, if I place a detector, we will find the blue side has come faster, or the red side has come later. They have changed, each of them have a phase difference between them, and then they reach at a delay time, delayed one to the other. The blue one is delayed more, or the red one is delayed more, depending on the way you place the gratings. So, how you want your dispersion. Basically, there is a delay in all these frequencies. So, I could have one grating and let all these wavelengths travel as long as possible until you reach the delay that you require. So, the delay means you are lengthening your pulse. But is that practical? That is not practical at all. So, what you need is you need one more grating. So, it passes through this these lenses. Now, these lenses act a bit like collimator. Okay. It sort of collimates the beam and it puts it onto this grating. So, what actually happens is I have suppose I have a circular beam, circular pulsed cross section. This is spatially. Once I put it on the grating, you will see the beam has become elliptical like this. Okay, and all the frequencies have spread out. Okay, the circular beam has become elliptical and all that has spread out. You can see it on the grating. Now, this elliptical beam has to pass through this telescope, so that it does not become a wider and wider ellipse as it goes through. As it goes through the air, you do not want it to become a much more elliptical thing. You need some control over it. Okay. So, that is why you need this telescope. It sort of this telescope maps this beam size, which is on this, onto this grating. It is giving the dispersion is happening, the frequencies have separated out and they have their own dispersion, but at the same time I map the spatial profile of the beam onto this grating. Okay. So, I have mapped it and it has come here. Now, this disperses once again, and the beams have become slightly more collimated after passing through this, and this is the picture that I get at this point after it has reflected off this grating or diffracted off this grating. So, this is the picture that I have here. Okay. But the disadvantage is I do not want an elliptical beam like that. It is very difficult to let such an elliptical beam pass through some more amplifiers which I have to do. I do not want it to pass through all those amplifiers. With this elliptical, it would have diverged out. Okay. So, a very convenient thing that happens is, if I allow this, if I put a mirror here and I allow this to pass back through this, if I pass it back through this, I do get a circular beam. In theory, it is absolutely a circular beam, but in actual practice, it may not be so. So, if I So, I have a double pass through this stretcher. That means one pass here, it goes here, it goes here, that is one pass. Then it goes back to this, goes back this way and then comes out. So, I have a double pass. So, the double pass not only gives me a double the group velocity dispersion, which I am looking forward to, but it also gives me a spatial cross section which is to my desire. Okay. So, I need this spatial cross section. Now, this spatial cross section, this is an actual beam taken from the laboratory, and you can see it is not actually round, there is some ellipticity remaining here, but this is the best that could be done. Okay. So, inherently the two gratings together, the stretcher on the whole, gives you an ellipticity which is involved. Even if you do a mathematical calculation, you will realize that it can be done, Fourier optics calculation can be done for the stretcher, and you will come to this conclusion that some ellipticity is brought about during its travel in the stretcher in such a configuration of two gratings here. And this part which is an ellipse like this is called the spectral walk-off, okay, because the spectrum has sort of walked off from its central position, and you pass it back once again, you should get back, the spectral walk-off should disappear. Okay. So, there are two reasons for having this double pass. One is to get a higher dispersion, double the dispersion, and you are bound to do it because you want the spectral walk-off to disappear. Okay. Now, because of that inherent astigmatism that is brought about by this grating pair, you can't get an exact circular beam, but you get a near circular beam. So, that is where the alignment of the grating is of these two gratings is important. Okay. Some of the aberrations here I have written, some of the aberrations due to mismatch of the incident angle. Okay. All these are aberrations, mismatch of the incident angle, okay, near lithro incidence, grating distance changes, non-parallel gratings, non-parallel grating grooves. Okay. So, what do I mean by non-parallel gratings? These are anti-parallel, but they have to be exactly anti-parallel, that means 90 degrees opposite of exactly parallel. And non-parallel grating grooves, okay, if I show the grooves like this of one, and the other one because of my placement may not be exactly perpendicular, may be at an angle, the grooves, then also if this is mismatched, then also you get not the ideal beam at the end of that pass. Okay. So, a lot of attention has to be paid to the alignment of this system. So, one could say that maybe the optical fiber is much better, you do not have to do that. But you can also say this, that I have so many parameters in my hand which I can control, okay, all these alignment procedures of the grating. So, that is an advantage. I have all that in my control, I can do it and get out a nice beam, while you do not have all those so many parameters to be controlled in an optical fiber. Okay. So, in that sense this can be an advantage, but the best reason why only grating stretchers are used nowadays is the compatibility of the stretcher and the compressor. They are conjugate with each other.